I work at AERONOVA in the General Design Department. As part of my role, I develop our objectives and the designs of our stratospheric vehicles. Previously, I worked with airships and stratospheric technology, but I'll say a few brief words about that a little bit later on, if I may. Right now, I'd like to take a moment to talk a bit about how humanity, throughout history, began to explore these remarkable altitudes. At the beginning of the last century, there was a truly strong and persistent desire to reach altitudes that humans had never reached before. There were many different and remarkable record-setting flights in airplanes and also in hot air balloons. There were many attempts, and many of them were unsuccessful and ended in tragedy. But nevertheless, humanity was very determined. In the end, all of this led to humans going beyond the atmosphere and starting to travel into space. The first steps were made with aerostatic devices. The fastest ascent to the stratosphere was achieved with pioneer Auguste Piccard, who built in 1931 the world's first stratospheric balloon. The USSR contributed, creating a stratospheric balloon in 1933 called USSR-1. After the war years, polyethylene envelopes were produced. Many countries mastered the technology of manufacturing large aerostats, and this became a distinct industry. Well, let's put it this way. The first satellites had only just appeared, but by that time, stratospheric balloons were already traversing the skies, flying around the Earth, flying over the Soviet Union, and being launched in large numbers. They were found useful for scientific tasks in space research and studying the Earth. Balloons to USSR. I listened to and spoke with a person who, back when he was working in the 5th Department of TSAGI, had someone bring in this balloon, this capsule, to figure out what it was. To create domestic stratospheric balloons, the Dolgoprudny Design Bureau of Automation was established and mastered high-altitude flight. There were also manned ascents. For testing, for example, spacesuits were used. Parachute jumps were made from those altitudes. In the Soviet Union, the Vega 1 and Vega 2 probes were launched. In 1985, they deployed balloons, and these balloons floated for several days. 2 balloon probes were launched in turn, first by Vega 1, then by Vega 2. They operated for 3 days each and flew around Venus. There was also a project for floating balloons on Mars. The European Space Agency was working on such a project in collaboration with Russian specialists. They even built a stratospheric balloon like this one, more precisely, an aerostat. It floated at a high altitude, near the stratosphere. Even now, there is great interest in ballooning on other planets, on Mars, Jupiter, Saturn, and especially Titan. I've also worked on this topic. It's the subject of my scientific research, and I defended my dissertation on it. For example, I wrote an article in Space Technology and Engineering where I talk about the kinds of exotic devices that are, in principle, being proposed for Venus. These devices have 1 or 2, and in some cases, even 5 or 6 envelopes that are completely filled with a special liquid that turns into vapor. These studies of planets, their atmospheres, and traveling through them with aerostats, all of that still lies ahead. Without a doubt, the future of space exploration belongs to these kinds of devices, including aerostatic ones. But at the same time, of course, for them to be able to float on other planets, they first need to be able to float here, at home. In order to master stratospheric topics and stratospheric vehicles, and to become world leaders, AERONOVA is now going to implement a program. I'm making a program for stratospheric vehicles. We are collaborating with many of our colleagues, my friends from the Moscow Aviation Institute. We have invited Arkady Dedkovsky, Ambilara Emilbaumova, and Denis Efremov, who has been working in this field for many years. The Dolgoprodny Design Bureau is also showing great interest and hopes that we will succeed.
Ilya, take it, and you need to carry it.
Just set it aside.
Together with the company AERONOVA, we are working on stratospheric launches of devices designed for long-duration flights. It's just fascinating for techies to figure out how to launch something to an altitude of several dozen kilometers and have it fly in stratospheric currents for tens or even hundreds of hours. Stratostats and weather balloons, which carry payloads and sensors into the stratosphere, are widely known. This is actually not really a particularly difficult task. Everyone has seen a balloon at some point in their life. If you let it go, it will simply fly up. A more challenging task is to launch something upward and have it stay there for more than a solar day. Let me explain. If you fill the envelope with gas, then as it rises up through Earth's atmosphere, it gradually starts to expand in volume, becoming noticeably larger as it ascends. The lifting gas, helium, expands, and at a certain point, at what's called the burst altitude, it fills the entire maximum volume of the envelope. After that, if the envelope is open at the bottom, a small amount of gas is released through the opening, and the stratospheric balloon continues to fly at the altitude it has reached. Or, if the envelope is closed or made of latex, it simply bursts, tears apart, and the flight ends. If the envelope is open, the flight continues until nightfall, because at night the cooled gas decreases in volume, its lifting force drops, and the device falls. That's why it's fairly easy to launch devices for up to 24 hours. It's not particularly difficult. If our goal is to have a flight last several days, and if we're talking about dozens of days, a month, or even more than a year, then with each day, the task becomes more and more technical, more and more complex. That's exactly the kind of challenge we started tackling a few years ago. When it comes to our field, long-duration stratospheric balloons, this is where the difficulties begin, specifically with the gases. In addition to the envelope that contains the lifting gas, an important component of a long-duration stratospheric balloon is the superpressure balloon. The overpressure balloon, the ballast envelope, they go by different names. We call it the overpressure balloon or bit. It is suspended beneath the gas envelope and, for example, air, nitrogen, or really any gas, such as helium, can be pumped into the ballast envelope. We use air from cylinders. The ballast envelope is spherical in shape. In our launches, it has a diameter of 3 to 4 meters, and its main purpose is to maintain a high internal overpressure. It holds several tens of kilopascals, depending on the specific task. This amounts to anywhere from a few to up to 10 tons of braking load across the cross-section of the spherical envelope. Why do we need to maintain high pressure, and how does the ballast envelope work? When the stratospheric balloon begins its ascent, the ballast envelope is not fully inflated. It has a kind of baggy shape. 20 cubic meter envelope has 4 cubic meters of air. As the balloon ascends to an altitude of 10 to 12 kilometers, this air, those 4 cubic meters, expands, and it expands to fill the entire volume of the envelope, so it becomes round. At that point, the pressure starts to increase, because the air inside the envelope has nowhere else to go and can't expand any further. And as the ascent continues, everyone knows Archimedes' principle. We all learned it in school, rho, g, v. The volume stays constant, g is constant, but the air density outside the ballast envelope keeps decreasing as you go higher. The atmosphere becomes thinner. And that's why the buoyant force acting on the ballast envelope decreases. Essentially, the ballast envelope becomes heavier as it rises. So, the excess lift we had at ground level gets balanced out. If we had 1 kilogram of excess lift, the ballast envelope created -1 kilogram with its additional weight. At this point, the craft has reached its altitude. The gas envelope hasn't completely filled the volume. It hasn't fully expanded. It didn't burst. Nothing happened to it. And from there we continue flying at an altitude determined by this balance. A bit higher during the day because it's warmer and the sun heats it up, which slightly increases the lift, providing just a bit more buoyancy, and a bit lower at night. As the lifting gas cools down, we drop lower. This is an envelope that has to withstand loads of several, or even dozens of tons of tension, and thanks to it, the stratospheric balloon doesn't reach its full expansion altitude, doesn't burst, and can continue its flight for months or even years. A double envelope design was used. Inside there's a hermetic liner made of a material that's not particularly strong but is gas tight, and on the outside there's a structural shell that actually bears the load. For the material of the outer shell, we used polyamide fabrics and polyester fabrics. They are widely used in the development and production of various bulletproof vests and structural components, and they have quite high strength properties, up to 3,000 newtons per 5 centimeters or even more. They performed excellently. All the shells we made from polyamide and polyester withstood their loads. The only thing that we actually changed during our research process was, in fact, the overall design of these shells. That is, the attachment points for external loads, the spots where we inserted the internal airtight liner, and the valve exit points, specifically. The internal airtight liner took up more of our resources. We probably tested about a dozen different materials, carefully evaluating them in terms of cost, tensile strength, and tear resistance. In the end, we found 2 working options that we still use today. The first option, as it turned out, is fabric with a thermopolyurethane coating, either Oxford or taffeta. The second option, which is more interesting to us, is multilayer polyethylene. The internal airtight liner is positioned relative to the outer shell at several points. Figuring out where these points should be located is one of the more challenging tasks, because as the process goes on, folds form. These folds straighten out when the outer shell stretches, which can be about 10 to 20%. At that moment, a leak can occur. If there's a leak, it means the altitude will drop during the stratospheric balloon's flight. And of course, the tests, which last at least 10 to 12 hours, always have a touch of romance to them. Testing during the launch means 2 very long, sleepless nights. 20 people are running around the test object and the shell around the clock, dealing with gas, ballast, launch payloads, fixing any inaccuracies or rough spots that come up right then and there. And of course, when you leave, say, the gas envelope filled overnight, you come back to the hangar at 4 in the morning just praying it hasn't ended up on the floor, hoping, too, that none of the seams have actually come apart at all. It's not a seam. Oh, a seam. It behaves that way in the cold. It just comes apart so easily. But this one is fine.
It was just a bad February. And here, it's coming apart.
And during the week, buying materials, cutting, welding, and then another night, which could end in either success or failure. That's how it is. And you never know where that finish line is, when you'll finally be sure you'll get the result, when the pressure doesn't change from day to day, and at the same time, that pressure is exactly what you need. It's an incredibly exciting event, especially after the device with this ballast shell first took to the sky, and you can see from the altitude chart that it reached the right level. Everything's perfect. For engineers, it might even be a little bit helpful to be naive, because if we hadn't been a bit naive a few years ago, we probably would have been horrified by the sheer amount of difficulties and problems we would face while working on this project. We went through a lot of different materials, spending considerable time carefully testing and evaluating each one, before finally finding the material that now successfully flies into the stratosphere with our launches. We manufactured our own shell entirely in Russia, using domestic materials, with a volume of 2,000 cubic meters. It underwent static and dynamic tests for gas permeability, as well as flight tests. It successfully met all the required specifications. Of course, there were some adventures along the way, but we managed to overcome all of them during this project. We also developed a payload that provides communication with the ground over distances of several hundred kilometers and enables recording and control of the onboard actuators. Therefore, in addition to the payload, long-duration stratospheric balloons often have launch shells. This is a latex shell with a volume of several cubic meters, which is filled with helium and suspended above the gas envelope, the main lifting shell of the stratospheric balloon. In order to have a high rate of climb safely and efficiently during the ascent to aircraft flight level, successfully. Accordingly, this allows us to leave the airspace where we might pose any danger or impose additional restrictions on other airspace users more quickly. At 14 to 15 kilometers altitude at burst, then the craft reaches its set altitude on its own lift. There are four main components, from top to bottom: the launch envelope, the gas envelope, the overpressure or ballast envelope, and the payload. What makes long-duration stratospheric balloons interesting is that they reach altitudes from 15 up to 30 or even 40 kilometers above the Earth's surface, and they are able to remain at those heights for extended periods of time, steadily carried along by the prevailing wind stream. In summer, this stream moves at speeds of several units, or even tens of kilometers per hour at altitudes of, for example, 20 kilometers. And in winter, inside the global stratospheric vortex in the northern hemisphere, it can reach speeds of up to 300 kilometers per hour. The stratosphere is a place where conditions can be predicted several weeks in advance. Periodically, these vortices break apart and then merge again. A stratospheric balloon, while at this altitude, migrates from one vortex to another. By changing the altitude of the device, you can move from one current to another, thereby adjusting the trajectory of the device, or, at certain latitudes, keep the device within a designated area. If we keep the device within a designated area, we can hang a signal relay over that area and provide communication, cellular, special purpose, or mobile. We can also monitor the territory over this area, and from an altitude of 20 kilometers, we can see all the way to the horizon, several hundred kilometers. A stratospheric balloon can cover up to 500 kilometers in one direction with its range, so a huge area is under it and within its field of view. And from one end of this territory to the other, you can provide communication through signal relay. This is interesting even without holding a fixed position. By being in the northern hemisphere and launching a group of stratospheric balloons, this could be 10 or even several dozen devices inside a stratospheric vortex, which is a stable circulation that occurs at latitudes of 60 to 70 degrees. If these circulation devices are distributed evenly throughout the area, then we can remain connected with at least one of these devices at all times, ensuring continuous coverage. And by ensuring communication between the devices within this group, we create similar satellite groupings. These groupings provide mobile communication, internet, transmission of certain specialized data, or, for example, monitoring of ice conditions along the Northern Sea route. In the same way, special communication systems are also used here. Stratostats and the stratosphere are often generally referred to as a backup layer. If something goes wrong with the satellites, or with the ground infrastructure, stratostats can be quickly deployed to the required area and altitude. And right away, they can take over the communication functions, serving as a backup for the satellite constellation. There's no conflict with satellites here. Satellites handle their specific tasks for a set period of time and for a specific budget. But there's another niche. There are other tasks that stratostats handle. The goal isn't to push satellites out of their markets. The goal is to open up a new market, the market for stratospheric vehicles.
That way. The wind is coming from there.
So right now, on a rather modest-sized stratostat, we're working out all of the issues of maneuvering, positioning, reaching a certain altitude, and maintaining that altitude. All of this is necessary in order to master navigation, first on regular, then on steerable stratostats. Then, to learn how to navigate using engines on stratospheric airships powered by solar energy. And to use all of this for flying in Earth's atmosphere, including for the exploration of other planets.
Don't drag the transmitter along the ground.
Moving through. Just keep it as taut as possible. That's all. Nine, 11, and 3.8 first.
Look, we're in haze.
There you go.
Now let's look. 177 kilometers. 170 to 180 matches our value.
And these are the trajectories we need to work through. Here are a few options. It could be this one, or maybe that one.